Okay, so for the second part, we're going to talk a little bit more about this idea of having a different approach, a graphical, numerical, algebraic approach. In the P chapter, we did quite a bit with the zero factor property for solving quadratic equations. If you remember that if we were just given some random quadratic equation like, let's say 3x squared minus 4x plus 15 equals 0, and our job was to solve that, okay, then we had a series of steps that we used to find the solutions to that. Okay, and the steps were we could use the zero factor property. Remember, one of the drawbacks with that was that in order for the zero factor property to work, okay, this has to be factorable. Okay, and are all quadratic equations factorable? No. Okay, so therefore this may or may not work. Okay, so in the order that you do this in is kind of up to you, but keep in mind that if I had to label this the zero factor property approach by factoring and setting the two factors equal to 0, okay, this would be algebraic. Okay, so that would be an algebraic approach to solving that problem. Okay, so this could have also been, remember, an inequality as well. Okay, we did a lot with that too. If that didn't work, then we had quadratic formula as an option. Okay, so we could take the A, B, and C and plug them into the quadratic formula. Okay, and if we had to label that, okay, we would also call that an algebraic approach as well. Okay, so that would be an algebra way to solve that problem. And both of those are good. This one is generally better because it's going to work with any quadratic equation, whether it's factorable or not. Okay, we also had completing the square as an option. I mentioned at the time, and I'll mention it again, if I had the quadratic formula at my disposal, I would probably never use completing the square myself. Okay, that doesn't mean you can't use it as an option to solve something. Okay, but I would not, if I had a choice, okay, I would probably use the quadratic formula before I use that. Okay, all right. And then we also learned about step 3 here would be a graphing approach. So graph and find the zeros. Okay, and remember the zeros, okay, are the x-intercepts. Okay. Now, keeping in mind that approach-wise, that would be from a graphical standpoint. So there's a graphing way to find the answers to this. But the one problem with this approach, though, that we discovered is that if we have a parabola and it has no x-intercepts, which is very well possible, okay, then is this going to be an option? Okay. The graphing approach would not work because there are no x-intercepts to find. And if we have a parabola that's vertex is above the x-axis, okay, and it opens up, it's not going to cross the x-axis, and therefore we're back to number 2, which is quadratic formula. Okay, we'd have to find that, and we know that we'd find imaginary answers. This is where we'd have a negative discriminant. Okay, so that graphing approach would not work. Okay, so it's a good approach sometimes to find solutions, but it doesn't always work because we don't always have real solutions. Okay, all right. We could also use a numerical approach here. Okay, a numerical approach would look at it like a table of values. Okay, because your calculator can produce a table of values. Okay, is it possible that we could look at the table and find out when the equation equals 0? Certainly. Okay. So again, the one question would be, is which of these approaches is the best? Okay. Well, ultimately that kind of depends on what the question is. If they ask you for an exact answer, then your best bet is either going to be numbers 1 or 2, because an algebraic approach is always going to give you exact answers. Okay, if they say approximately, okay, then a graphing approach would probably be a good choice. Okay, or a numeric approach looking at a table of values. Okay. All right, so a couple things we're going to talk about is if we look at this one, if they say x squared minus plus 4x minus 8 equals 0. So we'll use that same approach we did with our opener. We'll put everything on the same side. Okay, we could try to factor this. We could see if the other factors of 8 that would give us a difference of 4, this being a negative sign. So we got positive 8, negative 1, positive 4, negative 2, or vice versa on both of those would not produce a negative 4, or a positive 4, I mean. So therefore it's not factorable. So at this point, if I'm going to use an algebra approach, what's my I guess I got 2 choices really, but the best choice would be the quadratic formula. Once again, you could use completing the square, that's possible, but I would suggest if you have a choice to use quadratic formula. So if we were to use quadratic formula, it turns out to be negative 2 plus and minus 2 radical 3, same approach that we used here. And then if we looked at the decimals for these two, okay, we could check this by either putting the exact version or the decimal version into this and make sure it works. Okay, that numerical part would be a check. I'd put that under the numeric category. Okay, we're plugging them in and finding out what whether it equals 0 or not. The other thing that we could do here is we could graph this parabola and see when it crosses the x-axis. If we got these two for our x-intercepts, then we can be pretty sure that we did the algebra right also. Okay. But when we deal with that connection between algebra and geometry in this case, okay, a graphical approach and an algebra approach, okay, one thing that we make sure that we're clear on, okay, is that if we have any equation that's set equal to 0, okay, notice this doesn't have to be quadratic. We used a quadratic equation as our example, okay, but this could be anything. Earlier today we had an absolute value minus a radical equaled 0, and we went with the same approach. We've graphed it and we found the x-intercepts. True? So any equation that equals 0, okay, these three statements are equivalent. Okay? The first one is that the number a is a root or a solution of the equation f of x equals 0. Okay? So if we find the value that makes this equation true, that makes this equation equal 0, okay, then we found what we call a root, okay, or a solution. Okay, those two are synonymous. Number 2, okay, this number a is a 0 of the equation y equals f of x. Okay, so we can not only call it a root or a solution, we can also call it a 0. Okay, and what does that mean in terms of a graphical standpoint? The a that we find that is the root or the solution or the 0, okay, it's an x-intercept on the graph of f of x. Okay, all right. So sometimes the point a0 is referred to as an x-intercept. Okay, exactly what we just said here. So again, this is the connection essentially between the algebra and the geometry. If we find a value that makes this sentence true, okay, that on the graph, okay, that point is the x-intercept. Okay, so that gives us a couple of options for solving equations in general. In terms of finding the solutions, we can use an algebra approach and use the quadratic formula or factoring when it's quadratic, or if it's linear, okay, then we don't need that. We can just solve it like any normal linear equation. But bottom line is that these two things should match up. The algebra approach answer we get should match up with the x-intercept or x-intercepts of the graph. Okay. Any questions so far? All right, also in this section, there's a 4-step solving process that we generally use. We don't necessarily have to write out all the stuff that we're about to see for every single problem, but in general, this is a good set of steps that we can use to make sure that we solve any problem correctly. Okay, number 1, we want to understand the problem. So I'm going to give you look at a list here, and again, you don't need to write all these down because this is right straight from your book. Okay, so understanding the problem, there's a couple of good key pieces of information here that you should always try in terms of the understanding part. So read the problem as stated several times if necessary. So read the problem carefully. Be sure you understand the meaning of each term that's used. Okay, so make sure the vocabulary makes sense. If it doesn't, okay, ask or use the glossary. Step 3 here, restate the problem in your own words. Discuss the problem with others if you can. So try to, in your own words, okay, think about what are we really being asked here. Okay, because like I said, understanding the problem is generally one of the most important parts, because if we don't understand the problem, then it's going to be difficult to come up with a solution. So identify clearly the information that you need to solve the problem, and then find the information you need from the given data. Okay, so look closely at the information that you're given. Okay, and once you have a better understanding of the problem, then we go to step 2, which is to devise a plan. Okay, which for us is generally going to be to develop a mathematical model for this problem. Okay, we had some problems earlier that we did where I said draw a picture. Okay, especially if it has to do with some kind of shape. Okay, draw a picture is a very good strategy for problem solving. Okay, introduce a variable that represents the quantity that you seek, and keeping in mind there may be more than one. So if we're looking for some kind of time in the problem, okay, then maybe we use the variable t. Okay, if we're looking for an area, then we're going to use maybe variable a. Okay. And then the third step here, use the statement of the problem to find an equation or an inequality that relates the variables you seek and the quantities that you know. So the key issue is if we're going to develop this mathematical model, we want to try to take the information we're given and write a math sentence that makes sense in the situation. Okay. All right. Step 3. This is the carry out the plan part. Okay. Solve the mathematical model, okay, and support or confirm your solution. Okay. So if you can solve the equation that you write algebraically, that would be great. Okay. You may have to do it numerically or graphically. That might be a possibility where the algebra isn't something that we can solve with algebra. Okay. Or you can do it both ways and make sure both of them give you the same answer. Okay. All right. And then also solving numerically and graphically, because there is no other way possible. There are some equations like the one we did for the opener today that there isn't an algebra way to solve that. Okay. We have no choice but to use a graphing approach. Okay. But what's nice is that we have multiple approaches, and that's kind of what we're getting at today with our work. Okay. All right, and then step 4, interpret the solution of the problem, translate your mathematical result into the problem setting, and decide whether the result makes sense. Okay, a lot of times people get things wrong because they skip step 4 here. Okay, make sure that, I always say to add to this step is, okay, once you get an answer, okay, read the problem again and make sure that you've actually answered the question. Okay, because a lot of times we do some work and then we say, oh, that's it, and then we don't even actually read the question again, and therefore, okay, we may or may not have actually answered the question. So that's my advice on number 4, is reread the question when you get done and make sure that you've actually answered the question. Okay. All right, questions for me so far? Another part that in this section that we're going to talk about is sometimes that in a graph, okay, if we look at the equation here, I have 3 divided by 2x minus 5. If we look at the equation here and we want to say for instance, they said, what if 3 over 2x minus 5 equals 0, and we were supposed to find the solutions to that. Okay, well, if we were to graph that particular equation, 3 divided by 2x minus 5, okay, we can see that if we were to try to find the solutions to this, okay, it looks like it goes really close to the x-axis, okay, and then going towards this point in question on the right gets really small. Same thing here, as I'm going towards that point coming from the right, it looks like it gets big, and then as I go off to the right, okay, it looks like it gets close to 0. But remember, graph-wise, what am I looking for here? If I want to know the solutions to this equation, I'm looking for the x-intercepts of the equation on the left. Okay, but what do we see on the graph? Do we see any x-intercepts here? No. Okay, we don't see any x-intercepts. So is it possible that the answer to this would be no solution? Okay, would there be any x-intercepts here? Well, according to the graph, it doesn't look like there are. Okay, and if you think about it from an algebra approach, if this is a fraction and it equals 0, okay, in order for a fraction to equal 0, okay, we'd have to have something on the bottom, like let's just say 7 for instance, and we'd have to have 0 on the top. True? Okay, so 0 on the top would be the only thing that would give us 0. This could be anything. It could be a 7, or it could be, it could be an expression with variables in it. Okay, it could be -6. Okay, bottom line though is that in order for a fraction to be equal to 0, okay, we'd have to have 0 on the top. But on the top of this fraction is a 3. Okay, can this ever be 0? No, there's no variable here. Okay, if this were 3x, then it would be a different story, wouldn't it? Okay, then 3x equal to 0 would give us 0, and we would have an x-intercept that we'd see in the graph if we had changed that to 3x. Okay, so one thing to make sure we're careful on is that when we do work with a graphing calculator to find a solution to something like this, okay, that we're careful to recognize that there may not be an answer. Okay, again, it looks like these get close to 0, but they're really y equals 0 line is a horizontal asymptote for this particular equation. Okay. So as we work through this, we're going to get more experience with working with different types of functions, okay, and knowing that the graph of this, okay, is going to look something like this every time, translated essentially. Okay, all right. And the other thing I want to recognize here before we move on is that what's going on at this point right here. Remember, if we have this behavior where the bottom equals 0, if I have 2x minus 5, if we were to put 5 halves into this, okay, we'd get 5 minus 5, which is 0. And remember, it's not okay to have 0 on the bottom. Okay, so what does that produce in the graph here if we have that situation? And that would be an asymptote. Okay, these curves get infinitely close to that line, x equals 5 halves. Okay, but they don't cross that line. That is an asymptote that you see when you draw that graph. Okay. Question so far?